My name is Kayla Hornafius. I'm happy to share my research about using corn ethanol to make carbon-negative oil. I started this journey for my graduate research at Miami University of Ohio. Let me start off by explaining the process of enhanced oil recovery. It is the tertiary method of recovery that uses steam, or CO2, to produce oil from an exhausted reservoir. The CO2 is usually from a natural underground source, but recently there has been a strong interest to utilize anthropogenic CO2 that will then be permanently geologically sequestered. To do CO2 EOR, the CO2 is transported in a pipeline as a supercritical liquid. It is then injected into the reservoir as it sweeps across, it produces the oil, which is then shipped to market. The CO2 is recycled until the end of the project and is trapped permanently. Throughout the lifetime of a well, only about 60% of original oil in place can be produced. When the well is originally drilled, you recover about 20%. Later, water flooding is used to produce another 20%, and finally, CO2 can be injected to recover the last obtainable 20%. The CO2 acts as a solvent, making the oil trapped between the grains of sand expand, decreasing viscosity and repressurizing the reservoir. The remobilized oil flows to the existing well to be sold. First, I wanted to evaluate the fate of carbon in a bushel of corn used in ethanol production. The first step was to determine how much carbon was contained in a bushel of corn, and what became of it during the fermentation process. I discovered that about half of the carbon in corn goes into the ethanol we blend with our gasoline. A third goes into dried distiller's grains, which are used as livestock feed, and the remainder is emitted as carbon dioxide from fermentation. The CO2 emitted during the fermentation process is near pure, which makes it very suitable for enhanced oil recovery. Once I calculated the amount of CO2 fermentation emissions resulting from corn ethanol production, I could calculate the amount of CO2 being emitted by all of the Midwestern corn ethanol plants. It turns out that a huge amount of CO2 is being emitted. This anthropogenic source is bigger than the natural underground sources that currently supply the CO2 for all of Wyoming EOR projects. These CO2 emissions do not need to be reported to the EPA because they are biogenic in origin. It's understandable that the EPA doesn't require ethanol facilities to report their fermentation emissions because the same amount of CO2 that the corn captures from the atmosphere by photosynthesis is released back to the atmosphere during fermentation and by burning the ethanol in gasoline. This makes the corn ethanol process carbon neutral. However, if we capture these biogenic CO2 emissions and permanently sequester them in geological reservoirs, then the corn ethanol fermentation process would become carbon negative. In other words, we will be withdrawing carbon dioxide from the atmosphere. The next step in the analysis was to find out if the amount of CO2 sequestered in an EOR project was more than the amount of CO2 emitted when the resulting oil was burned. It turns out that lots of CO2 is needed to recover 1 barrel of oil. In terms of volumes, about 4 to 6 barrels of liquid CO2 at high pressure is needed to get 1 barrel out of the ground. The implication is that the oil itself is carbon negative if the CO2 is sourced from a corn ethanol plant. I then looked at where corn ethanol plants were located. The corn ethanol production in this country is very localized. There is almost no overlap between the Corn Belt and the oil basins in the U.S., which means that the CO2 from the corn ethanol plants will need to be shipped via pipeline to oil-producing states in order to make carbon-negative oil. This slide shows the current CO2 pipeline infrastructure and oil fields that are favorable to CO2 EOR. There are oil fields in southern Illinois and Kansas that are close to the corn ethanol plants, but the oil in these reservoirs are too shallow for CO2 EOR. However, Wyoming has a CO2 supply shortage and proven fields that are deep enough to reach the minimum miscible pressure, which is important for successful CO2 EOR. There's one example of fermentation emissions being used for EOR in this country and the world that I'm aware of. It is the Arcalin plant in Liberal, Kansas, and the CO2 is transported via pipeline across the panhandle of Oklahoma to the Booker oil field in Texas. Chaparral Energy operates the project. You can see from the Booker unit production history how CO2 EOR rejuvenates the old field almost back to the production levels of first oil. This is a huge financial incentive anywhere that this technology is being used. It's also a major potential consumer for corn ethanol fermentation emissions, as many existing wells in this country are suitable for EOR. I did an internship for the last 6 months with Elk Petroleum to explore the possibility for using corn CO2 for enhanced oil recovery. Based on this work, Elk Petroleum has proposed a pipeline that can gather the majority of CO2 currently being vented during the corn ethanol fermentation in Nebraska and Iowa and transport it to Wyoming. This would be about a 1,000-mile-long pipeline that would cost about $1 billion to construct. That sounds like a lot of money, but this is the lowest cost way to capture CO2 that has been proposed. Other CCS projects are far more expensive for the amount of CO2 that is being captured. So how could a $1 billion pipeline be constructed to accomplish all this carbon capture? It turns out that California has enacted a low-carbon fuel standard that awards carbon credits for low-carbon intensity fuels. So there's a carbon value chain that would take atmospheric CO2 sequestered by corn, growing, and ethanol production, store it in oil reservoirs in Wyoming during enhanced oil recovery, and utilize it in markets that reward low carbon intensity fuels like the LCFS. California is leading the front in establishing a low carbon intensity fuels market. The LCFS has committed the state to reduce the carbon intensity of its transportation fuels by 10% by 2020. The program was created to incentivize new technologies like biofuels and lower the carbon intensity of ethanol feedstocks. In its first year, the credit price rose dramatically due to uncertainty that current technology could meet the demand to reach the targets. This technology already exists. We are currently venting all the CO2 in the Midwest and not treating it as a valuable commodity, and this amount of financial incentive would pay the cost of sequestering all the corn ethanol fermentation emissions. If carbon credits are going to be used to provide financial incentive for collaboration between the oil and ethanol industries, the risk and reward will have to be evenly distributed. The x-axis is the price of raw CO2 that would be received by the ethanol plant from the oil companies. The y-axis shows the LCFS credit price that would be received by the oil companies for making carbon-negative oil. On the top right corner of this graph, the oil industry receives all the credits and pays the ethanol plant for its CO2, taking all the risk regarding the value of the credits. On the bottom left-hand corner, the ethanol plant receives the carbon credits and pays the oil company for the sequestration cost, assuming the risk. Somewhere along this line is a happy medium where the risk and cost allocation is balanced. To summarize, CO2 EOR produces carbon-negative oil and can potentially earn carbon credits for recognizing that this CO2 is no longer being emitted and is instead geologically sequestered permanently. It is a real potential source of additional revenue for the entire ethanol industry that would benefit the entire country and could form a strong partnership between the oil and ethanol industries. Thank you for the opportunity to speak with you today and my ability to share my research.